Okay, I guess we just wait for 3 more minutes, then we'll start a session.
Shan, can you hear me?
Yes.
Hi, this is Andy. Nice to meet you.
Hi, Andy. Welcome. Thank you.
How are things going?
Going well. We're just testing all the. Do you want to test sharing your screen first?
Absolutely, yes. Let me try that.
Yep, you should go ahead. You can go ahead to share the screen. It will automatically unshare mine. Perfect.
And you can see that okay?
I can see your screen, yes.
And it's filling your screen?
Yes, I think that looks perfect. And you can
good.
try to advance the slide to next slide. Perfect. Yes, everything looks perfect.
Okay.
All right. Okay, sounds good. And we're ready. And actually, we can stay on this screen because it's exactly the one.
I thought that's what we would do. I thought so.
Wonderful, wonderful. Yeah, about 1 more minute, then we can start. Thank you. So Andy, so I guess you know it's a 30 minutes there's the keynote session. So if you could speak for like 25 minutes and leave at least 5 minutes for question and answer. So we have enthusiastic attendees. I'm sure they come out with question for you.
And we have a town hall afterward too. So yeah.
Oh, that's great. Yes, because some of them might come up question later, and then they're trying to digest your talk, and then to type in a Q&A the question and then direct it to you, and you can try to answer them online in Q&A, and then also after the technical sessions, we also have a Q&A session, and you can, if you stay on until the time, you can also answer question live at the time.
Okay.
Thank you very much.
I should run about 25 minutes, I think.
Perfect. Thank you. Okay, a few more seconds. Okay, and then just checking that. So Amir, you got all those speakers for the technical session ready for the next session, Amir?
Yeah, let me check. There were 4 of them.
If you're still missing a few speakers, you can try to identify them from attendee list during Andy's talk.
I've been checking,
okay.
But
yeah. In the meantime, JC posts the chat message to all the attendees. So just want to say that if you are a speaker for the TS7 and you are in the attendees list, please identify yourself. You can raise your hand or send a chat message to us in the chat. And then one of us going to put you into panelists to get ready for technical session. All right, so without further ado, let's get started for today's first keynote session. Okay, so it is my greatest pleasure to have this opportunity to introduce you our first keynote speaker for today, as the Andy Daka. He's the CEO and co-founder of Momentum Dynamics. So Andy has an interesting bio that you can read it on the Huba website. And indeed, reading that is a fascinating story. And thank you, Andy, for sharing with us. So Andy was born in Brooklyn, New York, and then moved to Osaka, New York with his family. And then also moved to Hawaii, and then got educated college in Philadelphia. Okay. And then while in the Osaka, New York, actually his family developed best Italian restaurant in town. So some of our attendees from the Cornell University probably should take note of this to find out which restaurant it is. Andy has an interesting career, and then actually before he co-founded Momentum Dynamics, Andy did a lot of very interesting groundbreaking work at NASA for more than 20 years. So the few highlights that he's contributed to the design of International Space Station solar power array system. Also recently the Mars Pathfinder program in recent years, and also the future mission planning studies with NASA and also the United States Department of Defense. So Andy came upon the idea of the inductive charging while working on the International Space Station project. Found out that that's a very good way to save cable weight on the International Space Station and also future Mars missions. And why use those heavy cables, right? And why not just eliminate those instead of using electron and then use a vacuum to conduct the power. And then through this, founding of momentum dynamics and his career, then Andy developed strong capacity to identify engineering talent and manage a multidisciplinary engineering business teams. He's a member of IEEE and SAE, also served as a member of the standards committee. So Andy envisioned a world of zero emissions, zero cables, zero wasted mile, doing anything but making our life better. So he's working on making the world a better place, one electron at a time. So let's welcome Andy and learn more about his visions. So Andy, please go ahead.
Thank you, Jinshan, and thank you, Chris, and the organizers. I am absolutely delighted to be here at this conference again, and I hope next year or soon we will be able to reconvene in person and actually see each other again. So as often as we tend to meet virtually, and it has its benefits in some regards, I do miss meeting with you all, and I hope to be back with you soon. So let me begin this keynote, if I may, by diverting for a few minutes from the technical discussion of wireless power to speak more comprehensively on the matter of the commercialization of wireless power. I'll come directly to the point. The fascination we have with wireless power can no longer remain a technical preoccupation. It is time for wireless charging to be presented to the world as a compelling economic value proposition. It must be shown to enable new capabilities and simplify operations. It must be useful to all vehicle types and at all vehicle power levels. It must offer appreciable value. So wireless charging is not a mere convenience. To be clear, it is the capacity of wireless charging to deliver energy automatically and at low cost that establishes this value proposition. Let me elaborate. By now, I think it is clear to everyone that we have passed the tipping point and that vehicle electrification is no longer in doubt. For vehicles, it is now a matter of rate of adoption and removing the impediments to adoption. Charging is a key impediment to adoption. I would argue that electric vehicle adoption must happen quickly to support the production economies of scale that are necessary to produce affordable vehicles. But the impediment to EV adoption is charging technology and infrastructure. Charging, or electric fueling, as I like to call it, is the long neglected red-haired stepchild of electric transportation. Whether wired or wireless, the lack of charging points, of business models that really work, and the lack of uniform standards is hindering the more rapid adoption of electric vehicles. This problem is going to get worse before it gets better. So let me move on. For me, there is a strong analogy and lessons to be learned if we look back at the impetuous S-curve adoption of personal computers, the internet, and cell phones. All were similarly massive movements, and each influenced or enabled the others in various ways. Notice in this graph how computer adoption rises modestly at first, but then has a second inflection when it coincides with the internet. Then cell phones and the internet have nearly parallel steep rates of adoption. They clearly influenced each other, and both were enabled by the computer. At the pre-inflection stages of each of these movements, there was an inability of all but a few industry market analysts to imagine the disruptive market opportunities that would ultimately emerge and how they would interact synergistically to allow the market to grow. For example, the fabulous opportunities of search engines, streaming video, and the interactive virtual reality entertainment and interactive virtual reality entertainment were not generally appreciated in the 1980s or even the 1990s. While some people were concerned with chips and memory, others were creating newly enabled technologies that were almost unimaginable before. In this example, the compounding effect of these technologies worked to further expand and continually refresh the market. Perhaps this is a contributing factor to the increasing rate of adoption that is evident in these curves. And you'll notice that the curves become steeper over time. I envision wireless charging becoming an enabling technology in a similar way. EVs have created a need to rethink the way we deliver energy. Wireless charging will enable the expansion and growth of the EV market in ways that manual conductive charging cannot. We are at the inflection point of an S-curve of adoption right now. We simply need to encourage our peers to see the potential. And when I speak of electric vehicles, I mean all electric vehicles, not just passenger cars, but also trucks, buses, industrial vehicles, trains, autonomous vehicles, marine vehicles, construction, agricultural, and mining equipment, essentially every vehicle that moves packages, products, produce, and people. And usually they have wheels and sometimes they don't. My key point today is that we need a universal standard that is commercially viable across all of these vehicle types. These vehicles define the market. They have different requirements, but they will be propelled into the market by a universal automatic charging system and a robust industry standard for interoperability that has thus far not been promulgated. To achieve this, we must begin with a deep understanding of what the market will require. To some, the matter of EV recharging is already resolved. It is called a plug and it has a cable. In this commonly held view, the focus is on personal cars, while heavy-duty EVs are an afterthought to which people are now trying to force fit the fuel pump paradigm. As personal items, electric cars are considered no different than household appliances and all the other electric devices we have, tethered to power by a cable. Not only is this a narrow view of the concept of vehicle, it's an example of incremental thinking. It fails to meet the requirements dictated by the real physics of batteries and of human behavior. Plug-in charging cannot meet the operational and economic requirements of the market. In fact, plug-in charging makes electric vehicles less useful than their ICE equivalents. While understandable, this is the same sort of thinking that happens at the beginning of virtually every technological paradigm shift. It happened in the early 1900s in the transition from horse-drawn carriages to gasoline motor vehicles. In the 1800s, people fueled the horse-drawn carriages by providing a bucket of grain to a horse. When gasoline vehicles offered a new paradigm at the turn of the century, and before there were fuel pumps, people would buy a bucket of gasoline from a general store and fill a gas tank through a funnel. We simply carried forward the old fueling paradigm, even though it was not fitting to the new vehicle paradigm. We solved the bucket problem with a pump. The step change innovation back then was a pump and a hose. Today, we are repeating this linear thinking by using the same liquid pump idea to fuel a wholly different type of vehicle. We take a heavy cable, think of that as a hose, and we plug it into an electric vehicle to deliver electrical energy. But this does not fit because while it may take the same amount of time to plug in as it does to insert a pump nozzle, it takes hours to fully charge a battery. And that is where we see the essential need to get for automatic or automated wireless power. Oops. So, of course, the next logical step in this thinking was to increase the power level so that a battery can be filled with energy very quickly. And as we see in the progression on the slide, we go from level 2 to level 3 plug-in charging to increase the power level. But just like a gasoline fuel tank, I'm sorry. By increasing the battery to be filled very quickly with energy, we're thinking of the battery as though it were a fuel tank, but batteries are not fuel tanks. They cannot be. They cannot perform the same way. So let us look at the alternative, and that's where you see on slide 9 the automatic inductive charging system. And we'll go to the next slide, and we'll see an actual application. So let's say this. What if charging was automatic so that more frequent partial charging done opportunistically could add more energy than a single battery could hold from one charge? Here we see 2 examples of chargers supporting electric taxi operations in Oslo, Norway. Slide 10 shows our recent installation. This is a 75 kilowatt rated charger that is embedded in the pavement. There are 2 of them there. Those are the blue squares in the pavement. It is dedicated to taxi operations, electric taxi operations, and supports the taxi business by incrementally charging the vehicles whenever they wait at a taxi stand, as they ordinarily do. No time is wasted in bad weather searching for a plug-in charger. The vehicle automatically pairs with the charger once placed in park, and charging commences in about 4 seconds. Billing for energy for each car is automatically discriminated and logged to the charge point operator. This is the model for taxi electrification across Europe and beyond. In Norway, all taxis must be EVs by 2025. This is generally the pattern across the continent with strong mandates. It is the high utilization vehicle, the revenue sharing vehicle, that presents the most stressful challenge to vehicle electrification. And it's where we know from experience that plug-in charging does not solve the problem. So the next question for EVs is whether to try to fuel very fast or alternatively to fuel more frequently. If we fuel more frequently, but manually, human behavior dictates that the market will reject plug-in charging as the number of vehicles expands across the larger population. This has already happened in the fleet space. It has also been validated by recent reports with passenger vehicles, and I'll refer you to a recent AAA article that showed that 20% of new battery electric vehicle owners will not buy another battery electric vehicle, and the primary reason for the rejection is the charging problem. On the other hand, and I'll go to slide 12, if we fuel automatically, which is the decisive advantage of wireless charging, more frequent charging makes fueling as simple as automated toll collection is. And then something exceedingly valuable happens. The charging infrastructure begins to contribute not only to the performance and driving range of the vehicle, but also to keeping the cost of operating an EV as low as possible. So this slide that I'm showing now shows actual data. This is a data log, not a model, from a municipal bus installation that has been in operation since 2018. This happens to be a 200 kilowatt installation, but we've recently upgraded the transit agency with multiple new 300 kilowatt rated wireless chargers. While they're with the larger batteries these battery electric buses have, they require higher power levels. So we are fitting the need of the market in this case. The bus charges for approximately 5 minutes on each scheduled stop of the transit agency plaza. So the energy used for each route cycle is replaced in the 5-minute partial charge. The bus driver does not need to initiate the charging sequence, so the driver cannot forget to charge. The data log shows one day when the temperature was below freezing. Without the wireless charger, this bus would need to return to the garage for charging at midday, and then a second bus would need to come out and finish the day's driving. So 2 buses would need to be purchased to replace 1 diesel bus, and that is economically unsustainable. Notice that at the end of the day, after more than 12 hours of driving, the state of charge is 75%. As a consequence, Link Transit, the owner, no longer relies on plug-in chargers at all and uses the wireless system entirely. This also points to another important issue. Fleet operators are learning that the decision about which charging system to use should be made before deciding on which electric vehicle to buy. This is a reversal of the old way of doing things. But the right early decision has immense implications for achieving dramatic cost reductions compared to fossil fuels and compared to manual charging systems. This is the core of the value proposition of wireless charging. So I'd like to explain a little bit about the idea of modularity, but basically what you're looking at here is a system that is based on the concept of modules. They are easy to install, they are lightweight, they are suitable for mass production so that the cost of the system can be affordable to every owner, every use case. And that is the way we are proceeding, high power modular chargers. Let me go to say that ironically, at about the same time that people were fueling cars with buckets of gasoline, we also developed the electric transformer. Transformers are wonderfully elegant things. It is the air gap transformer which lets us rid ourselves of the cables of plug-in charging and transmit energy through air and water automatically. Nikola Tesla knew about air gap transformers when people were still feeding grain to their horse-drawn vehicles. To understand the potential for commercializing wireless power, one needs to recognize that it is more than a question of good fit, but also of economic imperatives. In fact, there are hidden costs to manual plug-in charging that can be avoided by automated wireless charging. For example, decentralizing charging and distributing it for certain types of fleets can have a dramatic effect on costs by reducing the number of electric vehicles needed to replace a diesel vehicle. Infrastructure build-out costs and personnel risk can be reduced dramatically. The same effect is seen when wireless chargers are shared and the number of chargers per vehicle is reduced, effectively increasing the utilization rate of the chargers. Not forcing a fleet operator to reorganize a transit bus parking lot to fit in all the plug-in chargers offers yet further cost savings and operational advantages. And what about the cost of personnel that would be needed to plug and unplug all those EVs every day? These are just examples, but the list of neglected costs of plug-in charging is quite lengthy. And many of these same advantages translate into the passenger vehicle market. These vehicles are not just cars. They are trucks, they are buses, they are industrial vehicles, trains, boats, and almost every form of transportation and logistics imaginable. Understanding this broad set of transportation uses and applications gives us essential insight into the technical performance requirements of wireless power systems. So there you see the interplay between the market and what the technology needs to do, and how we establish standards that make sense. In the final analysis, a winning technical solution must meet the real-world use case requirements for all of these applications. This is not an insignificant idea. It is the combination of two factors. First, automatic operation, and second, economic operation, that are genuinely transformative to an emerging electric vehicle market. Given this proposition, let me summarize what I believe are the essentials that the market requires. 1, wireless charging systems must be adaptable to all types of vehicles and rely upon the same protocols and communication systems so that they can be interoperable. This requires a modular system approach. 2, interoperability should be defined not only as the interoperation of wireless charging systems produced by different manufacturers, but additionally, so that a single ground-based charging system can be shared by multiple types of vehicles which operate the system automatically. This includes power level interoperability, not just vehicle type interoperability. Charger sharing is a crucial capability for the market. 3, these systems must be powerful enough to deliver a meaningful amount of energy during a short window that coincides with the routine dwell time for the users of these vehicles. This method of charging, opportunistic partial state of charge charging, keeps sufficient energy in the vehicle. As we all know, it is not necessary to completely fill a battery. This is how wireless charging infrastructure can contribute to the relief of range anxiety, especially in high utilization vehicles. 4, alignment, secure node-to-node communications, and safety systems must be fully interoperable across this range of vehicles. 5, the key to reduce total cost of operation or ownership is fully automated operation. This increases charger utilization rates and allows for distributed charger networks. In short, what we need is a universal definition of a wireless charging system that can adapt across the broad range of vehicle use cases. This is essentially what we have today with ICE vehicles, whether diesel or gasoline, regardless of vehicle type, regardless of use case. The fueling system is uniform and dependable. That is what we need in the new realm of electric vehicles. From a technical standpoint, all of this can be done by applying the basics of induction, even at low power level. Even at power levels above 300 kilowatts, magnetic field emissions around the perimeter of any vehicle, any type of vehicle, can be constrained well within ICNIRP 1998 limits. Power transfer efficiency, measured overall, well over 90%, better than most DC fast chargers, which rarely publish and almost never publish their efficiency, can be achieved. Driver guidance and alignment, autonomous vehicle integration, and simple installation have also been achieved. Let me conclude by saying that I believe we need to consider that charging does not need to follow the full, empty, full pattern of ICE vehicles. Instead, the idea that vehicles can simply charge themselves needs to be promoted. It has not yet occurred to many folks that EVs can charge themselves. We've seen this firsthand at our installations where there's an upsetting cognitive dissonance among drivers that this change presents. Some drivers who are used to filling up somehow think that they are being cheated if they drive away with less than 100% full battery, despite not having to exert any extra time or effort or even thought to refuel. What remains is to persuade the world that it's okay to give up the cord, to cut the cord. And if they do, EVs will truly be more affordable and better performing vehicles than any industry analyst today might be imagining. And I say thank you to you for allowing me the opportunity to speak to you. And I'd like to invite you all to our town hall where you see the address in blue. And I stand ready for questions. Thank you.
Thank you very much, Andy, for giving us this very interesting talk. Indeed, your idea of the automatic charging very frequently is I think that's very interesting. I think that's the way to go. So I want to remind the audience that you can type in your questions in the Q&A, okay? Or if you prefer to speak, you can raise your hand. I can turn on your microphone for you to speak. So either way, just use the Zoom features on your Zoom. On the lower part, there should be a raise hand icon and Q&A icon. Okay, so please utilize these two things. While waiting for the audience to ask questions. So I guess I have a question for you, Andy. Mm-hmm. So to do automatic charging, and then if the customer have to pay, so how does the infrastructure going to handle that?
Well, that's where the development of technology that focuses only on power sometimes neglects the essential need for secure communications, and begins with communications which then take advantage of existing protocols like ISO 15118 and others. So the ability to recognize, authenticate, and identify one vehicle from another is fairly straightforward process that we have implemented, and that we do that with every taxi and with every bus today, and have been for quite some time. Once you know the vehicle, you can associate the vehicle with an account, and you can charge the account in the same way that, let's say it's a utility company, has a registered list of users. The driver would have registered as a user in order to gain access to the charging system, and their account is charged for the electricity automatically and in the background. So in a nutshell, that's the simple answer. But we think that automatic billing for energy has to be part of the automatic delivery of energy.
Great, thank you very much. So I see that we have a question coming in from audience. A question asked by Wang Manuel. A question asked is that in terms of regions, in your opinion, which region is leading the way of electrification vehicles?
Well, there's no question that Europe is leading in terms of China is leading and has been for some time. Europe is moving very quickly. And then the United States is not as moving as quickly on cars until just recently. But I think what's happened in the electric bus market in the United States and in Europe and in China have moved things. It's the first vertical market that really inflected, and then we're now looking at the truck market inflecting very quickly. It's more difficult to do the trucks because they need a lot of power. And so this is where the real need for wireless power exerts itself and makes itself evident. Workers who operate these vehicles, these very large and heavy duty vehicles, are not happy about plugging them in. We have interviewed many of them, and it is an impediment to the adoption of these larger heavy duty vehicles. So the automatic delivery of energy there will actually speed up the adoption rate, we believe, of the heavy duty and fleet high utilization vehicles. They don't have to always be big trucks. They can be cars that are fleets as well. So that in turn tends to push on the regular passenger vehicle market. And we're seeing that happen today. So what region is leading? It's really hard to say, but I think you've now seen in the last, if you have been watching the stock market over the last 24 hours, the auto stocks are moving very quickly because their forecasts of vehicle buying habits are being upgraded. And that's because of their introduction of new electric vehicle models. We've been waiting a long time to see that happen. Now that it is, we have a problem with charging infrastructure that's inadequate to meet the need of new vehicle sales. So it's happening all over, really.
Thank you. So any other question from audience? Please utilize the opportunity. So maybe allow me to ask the time they allowed another question. So in your experience, okay, to make this a universal wireless EV charging come through, to set up this infrastructure, who should do that? The government or private entity? This is the kind of very large scale project, right?
No, not actually. I think you can find many examples where something similar to this has been done in other technology realms. If you are listening to this, you're using Wi-Fi or you're using Bluetooth or you're using USB, and all of those were industry standards that were developed rather rapidly when there was general agreement and belief that there was market demand waiting for that technology. And we have reached that point now. The traditional industry standard organizations may not be the best place for the standard to emerge.
Okay, thank you. That's one question coming up. I think is also interesting. I also want to ask that. How much, the question from King Seeds, how much does it cost to retrofit an existing EV to a wired charging system?
What kind of EV? So it's, we don't publish our prices. Those are usually in the public. Well, I'll give you an example. It's about $40,000 to outfit a bus. And that price is going to come down pretty dramatically, I think, in the next couple of years. That's due to the modularity of the system. As far as the ground station is concerned, they're anywhere from, they're pretty much on par on a per watt basis with DC fast chargers. So whatever thinking a DC fast charger should cost, that's about what a wireless charger should cost on a per watt basis. So, something on the order of 50 cents to 75 cents per watt. And in that realm, we also will see as volumes increase and the ability to adjust pricing to the market's needs changes, we'll see different pricing. But pricing structures are being established now as we have our conversations with many of the large fleet operators. So I can't give you a specific answer because it changes with each market.
Oh, all right. If we can take a few more minutes, sorry, another question coming. As we see in the slides, the pads are directly connected by public electricity network. Is that right?
Could you repeat that?
We see in the slides, the charging pad, the transmitter, directly connected to the public electricity network.
Are you talking about where the construction worker was installing the unit?
Something like that.
Let's go back to that. That picture?
Like
yeah. So there is a power electronics unit that supports that module, and it's connected directly to a 480 volt three-phase power supply from the utility company. And I will tell you that it's really no different than a DC fast charger in that sense.
Got it. Okay, very good. Thank you. I guess because of time constraint, we have to close this keynote session. And let's thank once again the Andy for giving a fascinating talk. Thank you very much, Andy.
It was my pleasure. Thank you.
Just, if you could stay on, because some of our attendees might have more questions for you. They might type in the Q&A. Thank you, Andy.
On. Thank you.
Hey, thank you. All right, so I'm turning over to session chair, co-chair for the technical session, the Professor Amir Mortazawi, also Professor Igor Pasifu. So you can take over from here. Thank you.
Hello, everyone. Thanks, Chen. Welcome to the session 7 on capacitive power transfer. Let me share the screen with you, if I could. Why this is not behaving correctly. Sorry. Allow me for a second. But the PowerPoint file opened and somebody sent a revised version of their PowerPoint as I was trying to replace the old version, something got messed up. Okay.
Yes, that's TS74.
Yes. Do you see?
So, I mean, my suggestion to use your old version, and when it comes to that one, you can just
yes, sure, yes. Somehow the whole thing got erased. So in the midst of doing it, that's why delay. But anyway, we can start. Do you see, first of all, the file I'm sharing with you?
I don't think you are sharing a screen.
How about that?
Yep.
All right. So again, welcome to Capacitive Power Transfer session. My name is Amir Mortazawi, University of Michigan, and co-chairing with Patrick Hu, University of Auckland. Let's begin with introducing papers. So the speakers have 2 minutes to present their paper summary, 1 page. So let's begin with the design of efficient double-sided LC matching network for capacitive wireless power transfer system. Li Fang Yi, Florida State University.
Thank you for introducing. Hello, everyone. This is Li Fang Yi from Florida State University. In our paper, we discussed about a method to design double-sided LC matching networks for capacitive wireless power transfer systems. Since the voltages across the metal planes on the same side, VCP and VCS are quite important for the transferred power and safety requirement. We focused on the ratio of these two voltages K and optimized this voltage ratio to maximize the efficiency of the matching network. First, we developed the voltage and current relationships inside the network with this voltage ratio K based on KCL and KVL. And then we discussed how this voltage ratio would influence the required inductance and capacitance in the matching networks. Based on the developed relationships, it is possible for us to determine the LC parameters once this voltage ratio is given. That means for each voltage ratio K, we can design certain double-sided LC matching networks to ensure this voltage ratio, the ZVS operation of the inverter stage, and the required output power. We have also discussed about the influence of this voltage ratio on efficiency and optimize this voltage ratio to maximize the efficiency of the network. To design the double-sided LC matching networks with a certain voltage ratio, we have developed three equations considering the design requirement. The parameters of the network can be obtained by solving this equation set in MATLAB. This paper provides a guideline on the design of double-sided LC matching networks, especially for the application where a certain voltage ratio of VCP to VCS is given. Also, it can provide information for an effective installation design of the primary and secondary sides. That's all. Thank you for your attention.
Thank you very much. So we proceed to the next paper, preliminary design by modeling. This is, they call it shielded capacitive power transfer. Typically, people are discouraged to invent acronyms, but in any case, system with inductance consideration. Ms. Ahmed.
Hello.
Yes, please.
Okay, hello everyone. I'm Suzanne Ahmad from Kyushu University, Japan. Okay, our title is Preliminary Design by Modeling SCPT or Shielded Capacitive Power Transfer. Actually, our goal is firstly to model, analyze, and design a CPT system for shielded capacitive power transfer, or we call also SCPT. Secondly, our purpose is to investigate the minimum inductance value in SCPT system. If inductor able to minimize in value, of course, loss and size can be reduced. Okay, we are going for the method, right? In which we are using the SCPT circuit with 6.78 megahertz as an operating frequency. Basically, in analysis, we are using the MATLAB software. And in resonance conditions, we found the relationship between inductor to capacitor, frequency, and load. We also do the experimental setup for validate our analysis pack. And now I'm going for the key result as in the slide. We found first relationship of inductor to other parameters, and we also obtain in analysis part the magnitude of currents, because this one for further investigations on the CPT system. And we investigate the effect of internal resistance of inductors on magnitude of currents. And based on the analysis, we found three possibility value of inductor as stated in the slide. And in conclusions, the difference value of inductance are attained in the resonance conditions. And secondly, the results show The internal series has significant effect in the total impedance in SCPT system and as resultant loss to the SCPT system. Thank you.
Thank you. The third paper is on modular-based photovoltaic system with contactless capacity power transfer interface from University of Auckland. Paper is given by Mr. Zhang.
Thank you, Chair. So the project motivation starts from providing a wireless interface for the PV system. And we want to provide a cheap wireless interface for the PV system and to get rid of the conventional installation and maintenance problem. As the primary research of this project, we want to develop a low power interface for the PV system. And in the PV system, in the whole system, we have an autonomous push-pull converter as the DC to AC inverter to drive the CPT interface. And we have an MPPT controller to adjust the DC to DC voltage duty cycle to ensure that maximum power has been transferred. And further increase the flexibility, the modules can be integrated on the DC side, on the receiving side. On the MATLAB result, we found a PV module rated at 25 watts can deliver about 20.6 watts to a DC load. And we also can be configured into a MISO system, multi-input single output system. We simulate with two modules, and it can totally deliver 38.1 watts to the DC load. And due to the series connection on the DC side, the MPPT controller for the duty cycle is slightly different. Our conclusion is that the proposed system can work both for the CISO and MISO configurations, and different modules can be connected in series of the rectification to add power. The experiment prototype is still under development for the future research. Thank you.
Thank you very much. So proceeding to paper number 5, titled Optimized Design of High Efficiency Emittance Matching Networks for Capacitive Wireless Power Transfer Systems from Cornell University. And Mr. Sinha.
Thank you, Chair. If you go to the next slides. So we know that we use matching networks in capacitive WPT systems to provide gain and compensation. Previously, we have presented efficiency maximization approach for our matching networks, but the topology for which this efficiency maximization was done, the output current of that matching network was dependent on the load. But as we know in battery charging applications, for constant current charging, we need load independent output current for a large dynamic range, voltage range of the battery. So in this work, we combine these two. We present a topology that provides the load independent output current and we maximize the efficiency of that. To provide load independent output current, we use what we call the emittance class of matching networks. This emittance class of networks, when excited by a voltage source, provide an infinite output impedance and therefore provides a constant current at the output, which is independent of the load. We use two types of emittance networks. One is LC3L network and one is LCLT network. In our system, at the central part, there is an LC3L network, which also consists of the capacitances of the coupler. And on both sides, primary and secondary side of that, there are LCLT stages. In the paper, we derive efficiency expression for the LC3L stage and the LCLT stages, and we derive the efficiency of the overall network and optimize it under the constraint that we have to go from a given input voltage to a given output voltage. The optimization results on the top right, as shown, is that in the primary side, the gains of all the LCLT stages in the optimal design comes out to be the same, and the gains of all the LCLT stages on the secondary side also comes out to be the same. However, the primary side stages provide a voltage step up and the secondary side stages provide a voltage step down. Therefore, their gains are reciprocal of one another. As it comes out of the optimization and is also intuitively explained in the paper, that the overall efficiency only depends on the total number of LCLT stages and not the individual number of stages on each side. And for a given total number of LCLT stages, you can find what's the efficiency, and there is an optimized maximum efficiency for a given total number of stages. To validate the approach, we built a 6.78 megahertz prototype with one LCLT stage on each side and a LC-QBL stage in the middle. And the right bottom plot here shown is actually loss in watts. And as we see that the predicted and measured losses closely match one another. So in summary, we propose to design an approach that maximizes the matching network efficiency in a capacitive WPT system that provides a load-independent output current. We presented the results of this optimization and we validated it experimentally. Thank you.
Thank you. The next paper on theoretical limits and optimal operating frequencies of capacitive wireless charging systems, gained by Cornell University. Mr. Maji.
Thank you. Can you please go to the next slide? So here what we are trying to find the theoretical power transfer limit of capacitive wireless power transfer systems and find if there is any optimal operating frequencies of these systems. So now the design of a capacitive WPT system involves the selection of a number of geometrical and electrical parameters, such as like the dimensions of the charging pad or the charging area, the system's operating frequency, the specifications of the matching network that we will use, and the selection of the semiconductor devices. Now, all these choices influence the power transfer limit and the efficiency of the system. So in the paper, we have first provided an analytical framework to derive the expression for output power of a capacitive WPT system in terms of its geometrical and electrical parameters. Now, this maximum or this power transfer limit is also constrained by a few like physical application specific limits. So the physical limits include like preventing the coupling plates from behaving as radiating surfaces, preventing breakdown of air in between the small like plate to AC or plate to ground air gap, and also maintaining the fringing electric fields within safety limits. And application specific limits include maintaining the thermal limits of the devices that we use. So once using this analytical framework, we can now have the results as shown here, the maximum output power as a function of the operating frequency for different WPT systems designed to charge EVs with 12 centimeter air gap. So you can see the maximum power here is achieved at a frequency of around 5 megahertz, while the system efficiency, which is shown in the paper, maximum system efficiency is attained around 11 megahertz. The another side to this is the size of the dimension of the matching networks, which goes down drastically as you go higher up in frequency. So another analysis we have done is like if we had better devices which had a lower RDS on or a lower output capacitance, we'll be able to achieve much higher power than we are with current devices. And to experimentally validate all these findings, we have designed a prototype 1 kilowatt system, which achieves a system efficiency of 88%, which is very close to the theoretical value. So to summarize, we proposed a framework to determine the maximum power transfer limit and the optimal operating frequencies. We have predicted and compared this limit for different systems, and we have validated this using a prototype 1 kilowatt DC to DC system. Thank you.
Thank you very much. I would like to remind audience that they could type questions. There is a question and answers button there. So please do so. And those can be then entertained at the end when we are done with the 2-minute presentations. So the next paper, tunable multi-state matching network for capacitive wireless power transfer system, Cornell University, and paper given by Mr. Hu.
Hello, Chair. So in this work, we propose a multi-stage tunable matching network to compensate for variations that is very common in dynamic wireless power transfer. And we know that for a large air gap capacitive wireless power transfer system, it's difficult to step up the voltage. So we usually need a multi-stage matching network. And to compensate for the variation in such system, in low power system, we can use some switch capacitor banks to compensate the variations in the coupler. But that's difficult in our large air gap capacitive power system because for a large power transferring through large air gap, usually there will be high voltage on the coupler plates. And therefore, the switch capacitor bank in this system will be used rated as very high voltage. And in this work, we combine the idea of switch capacitor compensation idea and the multi-stage matching network and propose a tunable multi-stage matching network. So with tunable multi-stage matching network, we can provide voltage gain stage by stage. And other than directly inserting the switch capacitor variable components directly with the coupler plates, we can insert the components at the intermediate stage of the multi-stage matching network so that the capacitors can be rated as low voltage, and therefore we can use higher figure of merit components such as better switches with low on resistance. And for the design methodology, we use a two-stage matching network as a design example, and we use the gain of the second stage as a control handle. If we increase the gain of the second stage, as you can see in the design method, the compensation range of the multi-stage matching network will fall. And however, if we decrease the gain of the second stage, the loss of the amplifier will also decrease. So in that case, combining the loss and the compensation range, we can say that the maximum compensation range of the coupler variation will be limited by the allowable losses, which will give us constraints on our component value selections. And for the experimental verifications, we use a 27 megahertz half-bridge inverter and ceramic capacitors to emulate the coupler plates. When we, as you can see on the key results, when we do not have any correction values for the intermediate stage of the variable components, the output current will fall dramatically when we change the coupler plate capacitance. And when we correct the values of the intermediate stage variable components, the voltage will be restored. And in summary, we propose a tunable multi-stage matching network that can compensate for the coupler variations. And we propose a comprehensive methodology for the design of the matching network and the component value selections. And also, we use a 27 megahertz prototype to verify our idea. Thank you.
Okay, thank you very much. The next paper is on a new coupling insensitive nonlinear capacitive resonance wireless power transfer circuit, the University of Michigan, and given by Ms. Won Choi. Go ahead, please.
Thank you, Professor. So hello, everyone. My name is Rain Chai, and I'm from University of Michigan. My research topic today is a coupling insensitive nonlinear capacitive resonant wireless power transfer circuit. So in a traditional linear resonant type wireless power transfer system, the transmitted power is a strong function of the relative position between the transmitter and receiver. And therefore it is very sensitive to the distance change between the pad. And in our research, the goal is to design a self-adaptive capacitive wireless power transfer system that can provide coupling insensitive power transmission. The method we use is to employ nonlinear resonators in the transmit side of the capacitive wireless power transfer circuit. The circuit operation can be described by nonlinear differential equations like listed in the slides, and with nonlinear capacitors in the system, the equation can be generalized into a special type of nonlinear differential equation, that is the Duffy equation. And this type of nonlinear resonators, circuit sensitivity to coupling capacitance value is greatly reduced. The experimental results comparing the performance of a nonlinear capacitive wireless power transfer circuit to that of a traditional linear type is presented. And the results shows that in a nonlinear circuit, output sensitivity to the mutual coupling capacitance is greatly reduced. So to sum up, in this work, a self-adaptive coupling capacitance insensitive wireless power transfer system is presented. And the simulation and experimental results shows that the coupling capacitance range that power can be effectively delivered is greatly extended in a nonlinear system. So such a nonlinear design can be applied in wireless charging of biomedical or implants or other applications where the relative position of transmitter and receiver could change. That's all, thank you.
Thank you. Next paper is on maximum available power of undersea capacitive coupling in a wireless power transfer system. Is given by Mr. Mahdi from Untitled University of Norway. So please, Mr. Mahdi.
Thanks, Professor Motozawi. Today, I'm going to talk a little bit about CPT system, but this time undersea water. In Norway, we are not only fascinated by electrical vehicle, I mean on-road electrical vehicles, as you saw already in the keynote presentation, but also we are fascinated by electrification of ships. And here at the University of the Arctic University of Norway, we are thinking of proposing wireless power transfer for charging these ships. And because it's like we think the CPT system is the best choice since it's cheap, better misalignment performance, lightweight, and low eddy current losses. But the problem, the power transmission or power transmit capability is very limited for a CPT system, and the separation distance between transmitter and receiver. That's why we thought it's better like to investigate first the capability of the system, how much available power we can transmit. And we used the conjugate image method to analyze the system. We submerged the system in water, so we increased the separation distance between the transmitter and the receiver. And then we tried to derive the equation based on two parameters. These two parameters is actually just a function of the couplers parameters, which is the capacitance and the conductance of the water. And the difference between this method and the previous method of analysis, it's we consider the losses of the water, because here we have a problem in the losses of the water. And then we derived, like we got like two, or the most important result we got, it's just 80% of the from transmitter to receiver we can transfer. And the system gives much better performance at lower frequency, which is this very important result than at higher frequency, which enable us to transfer more power with lower hazardous from high switching. And this is, we consider this maybe this is because of the ions on the seawater can help us like to transfer this. And also that the separation of the distance changing from 100 millimeter to 300 millimeters is actually not affecting the power transfer and the efficiency that much. That's why like we think we need to investigate more by proposing better, for example, good compensation circuit, and do more analysis with using proper inverter and rectifier to investigate further the system. Thank you very much.
Thank you very much. The next paper, a multi-receiver megahertz wireless power transfer system with hybrid coupler from Shanghai Jiaotong University. Paper is given by Mr. Shao.
Yeah, Chair, thank you. Thank you for introducing. So please move to next page. Thank you. Here, first, allow me to explain. My work is actually about IPT scenario, but maybe my coupler is a novel coupler, looks very capacitive. So I'm opportunate to this session. I'm glad to share it with you. And the main objective of my research is because, as we know, megahertz operation frequency can increase the spatial freedom of IPT, but and it tends to be more suitable for multi-receiver wireless power transfer scenarios. So this paper proposed a hybrid coupler to further improve the performance of multi-receiver transfer systems. And megahertz also have some unique technical challenges, such as potentially higher switching loss. So we introduce some soft switching topologies such as class E and class EF, but they are naturally of lower robustness. So this paper also proposed a novel methodology for impedance matching network design of megahertz IPT system. And about the method approach, as we can see from this figure, is the proposed hybrid coupler. Because conventional IPT couplers, they are both the transmitting and the receiving coils are of spiral shape, but in my coupler, the transmitting coil is of conventional spiral shape, but the receiving coil is of solenoid shape, and this can dramatically increase the space freedom of the transmitting pad, and it can allow more receiver in same transmitting area. And from the Smith chart, we can see the red curve, which is load impedance of the impedance matching network, can be directly calculated and transformed into the high efficiency load region, showing as the orange area in the figure. And the key result is the DC efficiency from one receiver to three receiver, and receiver is actually a LED strip, and the efficiency are between the range of 79% to 84%, and as we can see, the ZVS and ZVDS waveform is quite well performed. And so to summary, I proposed the hybrid coupler to improve the performance of megahertz IPT and an explicit element design method for megahertz WPT. And the proposed coupler and impedance matching network design method have broad prospects in other applications such as IoT and smart home. Thank you.
Thank you very much. And this was our 9th paper, the very last paper. So now we have some half hour or so to entertain questions and answers. I do not see any questions typed yet. Perhaps the audience could start typing their questions for the speakers. But there were already several questions asked prior to start of the session. So I'm going to read some of those questions and ask the authors to respond to them. And I hope the audience could then, in the meanwhile, type their questions. So there is one question, I believe. Well, not relevant. Let me move on to the next question. The question was asking, where is the session? A question on paper number 6, tunable multi-stage matching network for capacitive wireless power transfer system. The question is, nice presentation. I would like to ask, how will the location of variable capacitance affect the compensation range and the voltage stress of the variable capacitor? And I'm also curious why the coupling capacitor and secondary circuit in your prototype diagram can be directly simplified to RL. It seems that you are compensating CP instead of CS in your experiment. So this is a question on, again, paper number 6, tunable multi-stage matching networks for capacitive wireless power transfer system. So would the author would like to answer?
Hello, Chair. So I think there are several questions. The first question is about the compensation relationship between the compensation range and also the voltage stress on the variable capacitor. So basically, if we the compensation range, basically the voltage stress on the variable component is determined by the voltage gain that comes after the variable component. So the higher the voltage gain after the variable component, the smaller the voltage stress. And at the same point, the higher the voltage, the smaller the compensation range will be, as you can see in the method, the figure 3 in the paper, I guess. And for the second question, how can I simplify the secondary circuit into a capacitor and RL to emulate? So the way it works is for the architecture of the system is first is a voltage step-up circuit by a multi-stage mesh network, and then it's a current step-up circuit for the secondary side. So and for the large air gap system, the capacitance CS is very, very small comparing to CP. In that case, what we have on the secondary side is really having very small effect for the primary side. Therefore, we can use a capacitor and RL to emulate that. I hope that answered the question.
Thank you. There is one question for paper number 7, which is on new coupling in sensitive nonlinear capacitance, capacitive resonance wireless power transfer. The question is, would it be possible to adapt or combine this capacitive charger circuit for or with data transfer for implant application? So can data transfer also be incorporated into the design? So, yes, go ahead, please.
So far in our research, we were focusing on the power side, but I believe data transfer can also incorporate this type of design. I mean, the nonlinear resonator design, so that the system is less sensitive to this relative position change, and data can be successfully delivered over a certain distance.
Okay, thank you. There are a couple of questions that have been typed. I don't understand the first one. It says for the first speaker. So first author, please note, how did you decide the inductor values?
Hello. If I understand the question correctly, you mean how did I design the inductance for the matching networks? So actually all the parameters, the inductance, the capacitance are determined after solving the equation set. So first I developed the relationship between the inductance, capacitance and the voltage ratio. So referring to those developed relationship, we can build several equations which considering the requirement for the VVS, for the voltage ratio, and for the output power. So there are totally three equations, and there will be 3 unknowns in for the system. So by solving this equation set, we can determine the inductance, capacitance, and that means all the parameters in the matching networks can be determined. Thank you for your question.
Thank you. There is another question for paper number 7. It's on, I believe, it's the paper on nonlinear capacitor used in matching network. What is the ideal nonlinearity profile to maximize coupling independence?
So that is like kind of related to the design process. In our design, we first design a linear system, and then from the linear system, a nonlinearity profile, like as you mentioned, the voltage capacitance versus voltage, a nonlinearity profile can be numerically analyzed. I used MATLAB code to analyze this nonlinearity profile. So it exists, but it's a bell-shaped curve, which means the equivalent capacitance decreases as the voltage increases. But yeah, that's for the answer.
Okay.
Yeah, there's a related out live.
Go ahead.
Linear characteristic. Can you answer that too?
I'm sorry, could you repeat your
question?
Yeah,
there's a question, live question. Can you see it, or I can read it? For the paper on the linear capacitor used in the matching network, what is the ideal nonlinearity profile? Oh, that's the question you just answered, right?
Yeah, that's the question I just answered.
What sort of nonlinear components do you actually use? For example, if you use a diode, there could be very lossy.
If I use the diode, that would...
Yeah. So what the actual components?
Yes, I used varactor diodes. They are connected in anti-series, so they could withhold both positive and negative voltage. And I also put an inductor in parallel with them.
Yeah, so the question was on loss. In fact, quality factor is high. So we have prior publications which we can achieve the same efficiency as linear wireless power transfer system. So in fact, loss contribution is extremely small.
Okay, so comparable to normal linear components.
Yes, indeed.
Yeah,
yes,
they are comparable.
Yeah,
these are hyper-abrupt reactors, correct.
Thanks.
Any other questions? Let me go back again to the list of papers. Sometimes people type new questions and I have to update the No, I do not see any new questions. If any of the audience would like to ask questions, I can even allow them to speak if they raise their hand. Well, I have a couple of questions myself. Maybe.
Yeah, Amir, that's a hand raised by Yao Xia.
Oh, I see. Hand raised. I see. I cannot. I cannot.
Okay, Yaosha, you can just unmute.
Yes, I unmute myself. I have because I have posted a question on the website, but maybe my network is slow, so I prefer to ask by.
Go ahead.
Yeah, yes. I have a question to Shao Ge. Maybe can you answer my question, because I have read your paper, and I'm curious because you have mentioned you can synchronize the two transmitter using the controllers, but you mentioned you use the bootstrap self-drive. I mean PA or inverter. So I'm curious, how can you synchronize the two transmitter? Yeah, this is my question.
Okay, so basically, the thing is, autonomous push-pull converter, due to its own characteristic, it will synchronize by himself. So instead of like synchronize to the same phase, it will, with two modules, will have 180 degrees off. So that's being studied in previous IPT application. When we have three modules, it will have 120 degrees off each other. So typically speaking, we can't say it's synchronized to the same phase. It's like synchronized to 180 phase. It's like two modules providing power by turns. Did that answer your question?
So actually, you cannot control the phase. It's fixed, right? It's fixed to
yes,
100. Okay.
So
thank you.
So basically, when we use the autonomous push-pull topology, I can't control the phase. It will automatically go to 180 degrees. But if we use external control, then we can synchronize the phase to the same degree.
Yes, but external control is not a self-drive. It's not bootstrap anymore, right?
External control is not self-drive. Yes, you use external control signal to synchronize the two modules.
Okay, I see. Yes, thank you.
Okay, there is I think, new question type. That's a subsequent question to what's already asked, I think, from paper 1. That is, can you decide the inductance uniquely? Is the solution that you arrive is unique? That's for number 1.
Yeah. So referring to our methods, even the 3 equations seems to be nonlinear, but based on our experience, the inductance can be decided uniquely. Yeah.
Okay.
Thank you.
Thank you. Any other questions from audience?
A question to paper 6. So switched capacitor is used to achieve a variable capacitor. So, but for CPT, inductor, that's the tuning the system. Do you think it's easier to use a switched inductor instead of capacitor? How do you compare these two?
Yeah. So the idea of the switch inductor, we can also use that in the multi-stage this topology. And so the way we use reliable capacitor is because other than switch capacitor, there are also other phase switch capacitors that can be used at very high frequency with 0 voltage switching, which is easier to implement it.
Yeah, can we do switch the inductors?
Yes. Yes. In principle, there's no problem.
Mm-hmm. Thank you.
Any other questions?
Yeah, I have a question for paper 5. So theoretical limit, which is also related to another one, paper 7, no, paper 8, underwater CPT. So the question about theoretical limit. So basically, if we have ideal components, so the efficiency would always be 100%. And in terms of power, if it's a fully tuned, we can achieve constant voltage or constant current. If we change the load, we can achieve unlimited power transfer capability. But the reality is for IPT system, we know there's a KQ. There's a limit determined by KQ for maximum power and efficiency. So have you look at the Q quality factor, the effective quality factor on the system theoretical limit, power transfer limit? That's for paper 5.
Yeah, thank you for the question. Yeah, so so in this case, the losses that we have considered in the system are primarily the losses in the matching networks. So basically determined by the quality factor of the inductor that we use. And so the efficiency, the system efficiency that we have shown in the paper is based on mostly the losses in the inductors and whatever losses we have in the devices. So yeah, so the system efficiency, we see that we can achieve a maximum efficiency, like for this system, for the design systems, like 90%. And we that is for a particular choice of quality factor of the inductors that we have been able to achieve.
Did you look at the loss on the coupler?
No. So in this case, the only losses in the coupler are like we are using like Teflon as the insulation material for the charging pad, and the loss tangent for Teflon is pretty low. So the losses in the coupler is pretty low, like 0.1% of the total losses. So that's not a huge factor, like a huge fraction of the total losses.
Thank you.
Thanks. Any other questions? There is Mr. Mahdi, you have raised your hand.
Yeah, thank you very much. I just have a comment about, because the question also was about undersea water. And actually undersea water, we investigate also the maximum available efficiency, but unfortunately we didn't have like 100% like in water because of the conductivity of the water is the problem. So the maximum efficiency we achieved is actually only 80% also. It's depend, like if we transmit the power at the maximum efficiency, we lost the power, the maximum power, or if we transmit the maximum power, we lost the efficiency. So it's kind of like this, of course, this is like expected, but the problem, most probably, because if we increase the maximum efficiency, or the maximum efficiency is lost because of the conductivity of the seawater, because of the ions in the seawater.
Yeah, that's very interesting. You also mentioned about the frequency, right? Operating frequency. So you showed that you get higher power at up to 1.4 megahertz. Right? Is that what you showed?
It's actually, we tested the whole system based like from starting from 1 kilohertz to 1 megahertz. It's actually up to 10 megahertz, but it started self-resonating after 1.5 megahertz. So that's why we present only the results like until 1 megahertz. But whenever like we reduce the frequency, we notice that there's improvement in the efficiency and the power. And this is like, it's kind of like very fascinating or very interesting behavior of the seawater. Also, when we increase or reduce the air gap, or sorry, the gap is a perspiration distance between the transmitter and the receiver, also not changing. And we also like argue about this the problem because of the ions in the water. Can help, like because of free movement of the ions, it facilitate the free movement in the electric field.
Yeah, that's right. I'm just thinking, just wonder if we increase the frequency further, so in terms of power loss in the seawater, does it increase or decrease?
Of course, if we increase, we also studied, maybe it's not presented in this paper, but we studied the dissipation factor, which is basically is the Q. We can see how much the Q based on the dissipation factor, and we notice also dissipation factor increase with the frequency, because especially if we go for higher frequency ranges, we notice actually we have a problem of going into the problem of not only the epsilon or the permittivity, but epsilon prime and epsilon double prime, where it started at radio frequency range. So the permittivity of the seawater start changing, kind of getting. It's not maybe scientific way to say it, but it's going crazy when you increase the frequency.
Yeah, it's interesting. I don't know the answer, but I guess it's nonlinear. If you refer to induction heating, right? So induction heating, we want to have more power going to the metal. Then if you increase there's a sort of optimal frequency. Yes, that gives a maximum power. So I'm not sure in seawater whether there's also an optimal frequency that leads to the minimum loss.
That's very interesting. Actually, we should consider this in the analysis, because we didn't investigate the maximum and the optimum frequency, but at least we study over the frequency range just to see the behavior of the water. And it's very interesting because we also not only studied the seawater, we studied the fresh water, which is basically tap water, and there it's the different behavior because there's no ions, and so for example the capacitive, I give you some example, the capacitance of the seawater in nanofarad range, while the capacitance in the fresh water is just improve a little bit from the air gap. So air gap is like picofarad, maybe hundreds of picofarads in the fresh water, but we can go to seawater and suddenly in nanofarad. And we notice also for example, the capacitance, we can't use the famous formula, which is the permittivity multiplied by the area over the distance, because of the fringing, especially when you increase the fringing, it will be a very big problem in the seawater also. So that's why we try to derive a formula, so to at least to understand this behavior, because also with increasing the frequency, maybe also this is can answer some questions. And when increase the frequency, we increase the electric field, let's say, the problem of polymerization of the water molecules start increasing, and more electrons will be available in the water.
Yeah, it's very interesting. Thank you.
Yes.
Well,
thank you very much.
For questions and answers. We are getting towards the end of our allocated time. So thanks everybody. Thanks for speakers and the audience. And please, you can still continue typing your questions, and I'm sure the authors would be responding to them. But with that, I would like to close the session. Please remember the next session on safety of RF wireless power transfer technology. That will be starting 2 p.m. So with that again, appreciate attending the session on capacitive wireless power transfer, and have a good rest of the day. Goodbye now.
Thank you, Amir. So just remind the audience that the next session will start in 3 hours, and 2 p.m. is for the California, San Diego time.
Yes.
So see you in 3 hours.
Good for us. It's 6 o'clock morning now.
Okay, take a long break. Okay.
Yes.
That's good. Thank you.
Thank you.
Thank you again. Goodbye.
Bye.
Bye-bye.